Hello and welcome to Late Physics, where we dive deep into the mysteries of the universe, one concept at a time. If you're enjoying the journey, don't forget to like, subscribe, and hit that notification bell so you never miss an exploration into the fundamental forces that shape our world. Now let me ask you this. Where are you watching or listening from? Are you nestled in the comfort of your own home, or perhaps tuning in from somewhere far beyond your usual corner of the world? It's fascinating how light, that seemingly simple phenomenon, connects all of us, no matter where we are, at an astonishing speed of nearly 300,000 kilometers per second. And yet, there's so much more to the story of light speed, from the depths of space to the heart of theoretical physics. Today, we're going to embark on an incredible journey through the science of the speed of light, exploring how this constant shapes everything from the very fabric of space-time to our deepest theories about the universe. So sit back, relax, and let's dive into the deep physics of the speed of light. The speed of light is one of the most fundamental constants in physics, and it holds a place of remarkable importance in our understanding of the universe. It's the speed at which light travels through a vacuum, and it's universally the same for all observers, regardless of their motion or direction. This simple fact is actually one of the cornerstones of modern physics. In a sense, it's as if the universe itself is built upon the speed of the light. It sets a limit for how fast anything can travel, from matter to information, and it fundamentally shapes the nature of space, time, and reality itself. The concept of light travelling at a constant speed wasn't always so obvious, though. Early thinkers had many different ideas about how light might behave. Back in ancient Greece, for example, the philosopher Aristotle believed that light moved instantaneously. To him, light seemed like something that appeared at once, with no measurable travel time. In his view, light wasn't something that needed to travel at all. But as the centuries passed, scientists began to realize that perhaps there was more to the story. It wasn't until the 17th century that light's true nature started to reveal itself. Isaac Newton, the famous English physicist, proposed that light was made of particles. In his view, light particles had a definite speed, and their motion could be measured just like the motion of any other object. However, Newton didn't know just how fast light travelled. He suspected it might be incredibly fast, but without the tools to measure it precisely, it remained an open question. It was Olrumor, a Danish astronomer, who first provided experimental evidence that light actually had a finite speed. In 1697, Rømer was studying the moons of Jupiter when he noticed something peculiar. The time it took for Jupiter's moons to orbit the planet seemed to vary depending on the Earth's position relative to Jupiter. Rømer hypothesized that this difference was due to the finite time it took for light to travel from Jupiter's moons to Earth. By carefully measuring these variations, he estimated the speed of light to be about 200,000 kilometers per second, which is remarkably close to the value we know today. Rømer's discovery was groundbreaking, but it wasn't the final word. The 18th century brought new ideas about light, and one of the most influential was that of Pierre-Simon Laplace, a French mathematician and astronomer. Laplace proposed that light, while incredibly fast, was still subject to the laws of physics just like any other phenomenon. He also suggested that light's speed could, in principle, be measured more precisely through careful observation of celestial bodies. His ideas laid the groundwork for later experiments and theoretical advancements that would further solidify the concept of light as a finite and measurable quantity. As we move into the 19th century, the development of electromagnetic theory by James Clerk Maxwell was a pivotal moment in our understanding of light. Maxwell's equations, which described the behavior of electric and magnetic fields, predicted that light was an electromagnetic wave. And not only that, these equations also predicted that light travelled at a specific speed in a vacuum, around 299,792,450 meters per second. This was the first time that the speed of light was not just a measured quantity, but a number that arose naturally from the laws of physics. It was no longer just a curiosity or an experimental result, it was a fundamental feature of how the universe worked. But the true significance of light speed became clear only with the advent of Albert Einstein's special theory of relativity. Published in 1905, Einstein proposed something truly revolutionary: that the speed of light was constant for all observers, no matter how fast they were moving. This was a radical departure from the way we had thought about space and time. Before Einstein, People believed that if you were moving towards a source of light, the light should appear to move faster towards you. Similarly, if you were moving away, the light should seem to move slower. But Einstein showed that this wasn't the case. The speed of light remained the same no matter how fast you were moving. This insight led to the concept of space-time, where space and time are intertwined and fundamentally altered by the speed of light. Einstein's ideas had profound implications. They showed us that space and time were not absolute and fixed, but rather they could stretch and bend depending on how fast an object was moving. This was the beginning of modern physics as we know it, and it all hinged on that one constant, the speed of light. In fact, the very fabric of the universe, including the nature of time itself, is tied to the behavior of light. Today, the speed of light is much more than just a number on a piece of paper. It's central to everything from how we understand gravity to the way we communicate through fiber optic cables. It's a key factor in the equations that describe the universe's expansion and the behavior of black holes. And as we continue to explore the deepest corners of space, we find that the speed of light is one of the fundamental limits that shapes the way we can observe and interact with the cosmos. In this exploration, we will journey into these deeper topics, from relativity and quantum mechanics to the mysteries of the universe itself. The speed of light isn't just a number, it's a key to understanding the very nature of reality, and in the chapters ahead, we will unravel its role in shaping the cosmos, from the tiniest particles to the vastness of the universe. In the late 1700s, a breakthrough came that forever changed our understanding of light. For centuries, scientists had speculated about the nature of light and its speed, but it wasn't until the Danish astronomer Ole Rømer made his remarkable discovery in 1697 that the speed of light was measured for the very first time. Rømer was studying the orbits of Jupiter's moons, specifically Io, when he noticed an intriguing pattern. The time it took for Io to complete its orbit appeared to change depending on the Earth's position in its orbit around the Sun. When Earth was moving away from Jupiter, the apparent time for Io's orbit was delayed. When Earth was moving towards Jupiter, the timing was slightly faster. Rømer realized that this change in timing was due to the finite speed at which light travels. He proposed that light had a delay in reaching us, depending on how far Earth was from Jupiter at any given time. By carefully calculating these differences, Rømer concluded that light took about 22 minutes to cross the diameter of Earth's orbit. From this, he made the first estimate of the speed of light, which was roughly 200,000 kilometers per second. This was remarkably close to the modern value of the speed of light, which is about 299,792,450 meters per second. Rømer's work, though crude by today's standards, was a groundbreaking moment that paved the way for more accurate measurements in the years to come. Fast forward to the 19th century, and the task of measuring light speed was still a major challenge. Enter the French physicist Armand Fizeau. In 1849, Fizeau conducted a revolutionary experiment that would improve upon Rømer's earlier estimate. He used a technique that involved a rotating cogwheel and a distant mirror. Fizeau sent a beam of light through the gaps in the rotating wheel, bounced it off the mirror and timed how long it took for the light to travel to the mirror and back. By adjusting the speed of the wheel's rotation, he was able to calculate the time it took for the light to travel the known distance to the mirror. Fizeau's experiment gave a much more accurate value for the speed of light, around 330,000 kilometers per second. This was very close to the modern value, and it marked a major leap forward in the precision of measurements. However, Fizeau's method was still not perfect. The next major improvement came from a colleague of his, Albert Michelson, who would go on to become famous for his work in measuring the speed of light with even greater accuracy. In the 1870s, Michelson took Fizeau's idea and refined it further. He used a rotating octagonal mirror, which allowed for more precise measurements of light's time of travel. Michelson's improvements led to measurements that were even closer to the true speed of light, and his work earned him the Nobel Prize in 1923. But while scientists like Fizeau and Michelson were perfecting their experiments, there was still a fundamental question lingering in the background. What was the medium through which light travelled? In the 19th century, many physicists believed that space itself was filled with a substance called the ether. This hypothetical ether was thought to be the medium through which light waves propagated, much like sound waves travel through air. The idea was that light needed something to carry it, and the ether was the best candidate. In 1887, Michelson teamed up with Edward Morley to test the existence of this ether. Their famous experiment, known as the Michelson-Morley experiment, was designed to detect the Earth's motion through the ether by measuring the speed of light in different directions. They expected to see a difference in the speed of light depending on whether the Earth was moving towards or away from the ether. However, the results of the Michelson-Morley experiment were nothing short of baffling. They found no difference in the speed of light, regardless of the direction the light travelled. This failure to detect the ether was one of the key pieces of evidence that led to the eventual abandonment of the ether theory. In 1905, just a few years later, Albert Einstein introduced his special theory of relativity, which radically redefined our understanding of space and time, and showed that the speed of light was constant for all observers, no matter how fast they were moving. This groundbreaking idea eliminated the need for the ether altogether and laid the foundation for modern physics. But before all of this, the precision in measuring light's speed had already been advancing rapidly. One key figure in this advancement was the German astronomer Friedrich Bessel. In 1838, Bessel successfully measured the distance to the star 61 Cygni, a distant star in the constellation of Cygnus, using parallax. This method involved observing the star from two different points on Earth's orbit to measure its apparent shift in position. This was the first accurate measurement of a star's distance in space, and it helped to establish the scale of the universe. Bessel's work was indirectly related to light speed measurements, because by accurately determining the distances to stars, astronomers could better understand the time it took for light to travel those vast distances. Bessel's success in measuring stellar distances provided the necessary framework for later astronomers to measure light's travel time across these vast expanses. In fact, his work helped to refine our understanding of the scale of the universe, which in turn influenced our measurements of light speed. While Rømer, Fizeau, Michelson and others were working on measuring light speed here on Earth, the larger question of how light fits into the grand scheme of the universe was beginning to take shape. These early efforts in measuring light speed set the stage for the modern understanding of light as a universal constant, paving the way for the deeper explorations in relativity, quantum mechanics, and cosmology that followed. Each step along the way, from Rømer's first estimate to Michelson's precise measurements, brought us closer to understanding the true nature of light and its role in the universe. And while there are still mysteries to explore, such as whether light might behave differently under extreme conditions like near black holes or in quantum systems, the story of how we measured light's speed is one of gradual discovery, with each new insight building on the work of those who came before. It's remarkable to think that, over the course of just a few centuries, we went from assuming light travelled instantaneously to having a precise understanding of its speed. Today, this constant plays a crucial role in everything from our ability to send signals across vast distances in space to the fundamental theories that govern the structure of the universe. The history of measuring light speed is not just a tale of scientific discovery. It's a story of how human curiosity and ingenuity continue to push the boundaries of what we know about the world around us. In the mid-19th century, a monumental shift occurred in our understanding of light and its place in the broader realm of physics. It was James Clerk Maxwell, a Scottish mathematician and physicist, who provided the key to unifying two seemingly unrelated phenomena, electricity and magnetism. Maxwell's insight into the deep connection between these forces gave rise to the theory of electromagnetism, which not only described the behavior of electric and magnetic fields, but also laid the foundation for understanding light as an electromagnetic wave. Before Maxwell, electricity and magnetism were considered separate fields, each with its own laws and principles. André-Marie Ampère had developed a theory that described the relationship between electric currents and magnetic fields, and Michael Faraday had discovered that changing magnetic fields could induce electric currents, an effect known as electromagnetic induction. However, these discoveries existed in isolation, with no unifying framework to explain how electricity and magnetism were connected, especially when it came to phenomena like light. Maxwell's genius was in recognizing that electricity, magnetism, and light were all part of the same underlying phenomenon. In 1864, Maxwell published his equations, a set of 4 mathematical formulas that described the relationship between electric and magnetic fields and their interaction with matter. These equations showed that electric fields and magnetic fields could not only exist independently, but could also propagate through space in the form of waves, electromagnetic waves. And the key insight: light itself was an electromagnetic wave. This was a groundbreaking realization, as it unified the previously separate domains of optics, electricity, and magnetism into a single, cohesive theory. Maxwell's equations predicted that these waves, which included visible light, radio waves, microwaves, and X-rays, all traveled at the same speed, the speed of light. This was an astounding connection because it suggested that light was just one type of electromagnetic wave, not some mysterious or fundamentally different phenomenon. Light, as it turned out, was simply an oscillating electric and magnetic field propagating through space, travelling at a constant speed in a vacuum. But while Maxwell's equations were revolutionary, they remained just a theoretical framework until they were experimentally confirmed. This came in 1888, when the German physicist Heinrich Hertz set out to prove Maxwell's theory. Hertz constructed an apparatus that allowed him to generate electromagnetic waves in the laboratory. Using a spark gap transmitter and a receiver, he successfully demonstrated the existence of these waves, showing that they travelled through space at the speed predicted by Maxwell's equations. Hertz's experiment was the first to conclusively confirm that electromagnetic waves, including light, were real and that their speed could be measured in the lab. Hertz's work not only confirmed Maxwell's theory, but also opened the door to an entire new field of electromagnetic research, leading to the development of radio, television, and later wireless communication technologies. His experiments also hinted at the nature of light itself, its wave-like behaviour, laying the groundwork for future discoveries in optics and quantum mechanics. In the decades that followed, Maxwell's equations were refined and made even more accessible by a series of brilliant scientists, including Oliver Heaviside and Gilbert N. Lewis. Heaviside, an English electrical engineer, simplified Maxwell's original equations, removing some of the cumbersome components and expressing them in a more manageable form. His work was crucial because it made Maxwell's equations more practical for engineers and physicists working with electromagnetism in real-world applications, from electrical circuits to radio transmissions. At the same time, Gilbert N. Lewis, an American chemist and physicist, contributed to the understanding of electromagnetic waves by linking them to the quantum theory of light. Lewis was instrumental in developing the concept of the photon in the early 20th century, providing a bridge between the classical wave theory of light and the emerging quantum mechanics. He also expanded on Maxwell's equations by exploring how electromagnetic waves could interact with matter at a molecular and atomic level, setting the stage for future discoveries in quantum electrodynamics. Despite these advances, the true connection between electromagnetism and the quantum world was not fully understood until much later. This gap in understanding led to speculative ideas about the nature of light. One of the most influential figures to explore these ideas was Paul Dirac, an English theoretical physicist known for his work in quantum mechanics and the theory of quantum fields. Dirac speculated on the relationship between electromagnetic waves, including light, and quantum field theory, which treats light not only as a wave but also as a particle. This notion, that light could behave as both a wave and a particle, would later become a cornerstone of modern quantum mechanics. Dirac's work suggested that the behaviour of light could be explained by a quantum field, and that photons, the particles of light, were a fundamental aspect of how electromagnetic waves interacted with matter. His ideas helped to form the basis of quantum electrodynamics, a theory that describes how light and matter interact at the quantum level. This was a far cry from the classical view of light as a simple electromagnetic wave, but it was a crucial step in understanding the complex dual nature of light, which would be further developed by later scientists like Albert Einstein, Niels Bohr, and Werner Heisenberg. Maxwell's equations, Hertz's experimental confirmation, and the contributions of Heaviside, Lewis, and Dirac all played pivotal roles in shaping our modern understanding of light. They showed that light was not a mysterious, isolated phenomenon, but rather a form of electromagnetic radiation governed by the same laws that apply to electricity and magnetism. The implications of this were far-reaching. It meant that light could be understood in the same framework as radio waves and X-rays, and it also opened the door to the field of quantum mechanics, where the wave-particle duality of light would be explored in depth. Maxwell's unification of electricity, magnetism, and optics into a single theory revolutionized not only our understanding of light, but also the way we view the universe itself. Light is no longer just a phenomenon that we observe, it is an essential part of the electromagnetic spectrum, a key player in the interactions that govern everything from the behavior of atoms to the structure of galaxies. In a very real sense, the study of light is the study of the universe's most fundamental forces, and it is through light that we're able to probe the farthest reaches of space and uncover the secrets of the cosmos. In 1905, Albert Einstein published a groundbreaking paper that would forever change the way we understand space, time, and light. This was his special theory of relativity, and it introduced ideas that were as revolutionary as they were profound. The core of Einstein's theory was simple yet incredibly bold. The speed of light is constant for all observers, regardless of their motion or the motion of the light source. This single insight transformed our understanding of the universe and laid the foundation for much of modern physics. But while Einstein's name became synonymous with relativity, his work was built on the contributions of earlier scientists who had been wrestling with similar ideas for years. Two of the most important figures in this intellectual journey were Henri Poincaré and Hendrik Lorentz. Poincaré, a French mathematician and physicist, had already begun to question the established notions of space and time in the late 19th century. He realized that the laws of physics might need to be modified in order to account for the fact that the speed of light seemed to be the same for all observers, no matter how fast they were moving. Poincaré also worked on the concept of relativity, though his ideas were not as fully formed as Einstein's would later be. He proposed that the laws of physics were the same for all observers moving at constant speeds, which was a key idea that would later become central to the special theory of relativity. However, it was Hendrik Lorentz, a Dutch physicist, who developed the mathematical framework that would eventually allow Einstein to formalize his theory. Lorentz introduced what are now known as Lorentz transformations, which describe how measurements of space and time change for observers in relative motion. These transformations showed that time and space were not absolute. They could stretch and compress depending on the relative motion of the observer. This was a significant departure from the classical view of space and time as unchanging universal backgrounds against which events occurred. Lorentz's work, which focused on the effects of motion on the speed of light, set the stage for Einstein's final theory. In fact, Lorentz's ideas were so closely tied to the speed of light that he introduced the concept of length contraction, the idea that objects appear shorter in the direction of motion as they approach the speed of light. While Lorentz viewed this as a consequence of the so-called ether, the medium once thought to carry light waves, Einstein's special theory of relativity would later eliminate the need for the ether entirely. Still, Lorentz's work was instrumental in showing that space and time were much more malleable than anyone had previously imagined. Einstein's genius was in realizing that these concepts needed to be applied universally, not just to light or electricity and magnetism, but to all physical phenomena. He proposed that the speed of light is constant for all observers, and that no object could travel faster than the speed of light. This notion of a universal speed limit was a radical departure from the Newtonian view of space and time. In Newton's framework, time was absolute, and space was a fixed stage upon which events unfolded, but Einstein's theory showed that time and space are intertwined in a flexible fabric, which we now call space-time, and that this fabric is distorted by mass and energy. One of the most profound implications of Einstein's theory was the concept of time dilation. This refers to the way time appears to pass more slowly for objects moving at speeds close to the speed of light. The faster an object moves, the slower time appears to pass for it relative to an observer at rest. This effect is not just theoretical. It's been experimentally verified using highly precise clocks. For instance, atomic clocks flown on airplanes have shown that the faster the plane moves, the slower time passes on board compared to clocks on the ground. The effects of time dilation become significant only at speeds close to the speed of light, but they are a direct consequence of Einstein's ideas. One scientist who helped to further explore these effects was Lise Meitner, an Austrian-Swedish physicist. While her most famous contributions were in nuclear physics, she also made important observations on time dilation and how it related to the speed of light. In the 20th century, as quantum mechanics and relativity began to converge, Meitner's work on the atomic nucleus and her understanding of the principles of physics under extreme conditions further contributed to the understanding of how time and space behave at relativistic speeds. Her research helped clarify how Einstein's theories could be applied to particles moving at near-light speeds, an area that would become crucial in the development of nuclear energy and particle accelerators. But what happens to light itself when it approaches these relativistic speeds? Does light slow down? Einstein's theory answered this with clarity. No, the speed of light remains constant no matter how fast the observer is moving. This constancy is what makes light so special and central to the theory of relativity. It also means that, unlike other objects which experience changes in their speed due to motion, light does not slow down or speed up. It always travels at the same speed, 300 million meters per second, in a vacuum. Max Born, a German physicist who made significant contributions to quantum mechanics, helped to extend Einstein's ideas into the world of quantum theory. Born was one of the pioneers in interpreting quantum mechanics probabilistically, and his work on the mathematical framework of quantum theory also touched on the role of relativity. He helped to shape how we think about the relationship between energy, mass, and the speed of light in the context of quantum particles. One of Born's key contributions was his interpretation of the energy-mass equivalence that Einstein proposed in his famous equation E = mc squared. This equation, often called one of the most famous equations in physics, shows that energy and mass are interchangeable. A small amount of mass can be converted into a large amount of energy, and vice versa. Born's work helped to further solidify this relationship and showed how it could be applied to understanding the behavior of particles at high speeds, including those moving close to the speed of light. But Einstein's theory didn't just change the way we thought about time and space. It also had a profound impact on our understanding of the universe. The idea that the speed of light was a fundamental constant meant that space and time were not as separate as we had once thought. Instead, they were intertwined in a four-dimensional fabric that could be warped and stretched by the presence of mass and energy. This new way of thinking about the universe not only changed the field of physics, but also influenced the way we view reality itself. The work of Poincaré, Lorentz, Meitner, Born, and of course Einstein, has helped us to better understand the fundamental principles that govern the cosmos. Their combined contributions have shown that light is not just a phenomenon to be observed, but a key to unlocking the mysteries of space, time, and the very fabric of the universe. The special theory of relativity is not just a theory, it is the foundation of much of modern physics, and its implications continue to shape the way we explore and understand the universe today. The speed of light, measured at nearly 300,000 kilometers per second, is one of the most well-known constants in the universe. It's more than just a number, it's fundamental to the way we understand the structure of space, time, and the laws of physics. For over a century, this constancy has been a cornerstone of both Einstein's theory of relativity and modern physics in general. The idea that light travels at the same speed, regardless of the observer's motion or the source's motion, has shaped our understanding of everything from gravity to quantum mechanics. It's become so ingrained in our physics that it often seems unshakable. Yet, as with many scientific ideas, questions have arisen, challenging our perception of this universal truth. One such challenge comes from the work of Joachim Schwindt, a physicist who has explored the possibility that the speed of light may fluctuate under extreme conditions. Schwindt's research has suggested that in environments with incredibly high energy or intense gravitational fields, the speed of light could potentially vary. This idea stems from attempts to reconcile general relativity and quantum mechanics, two powerful theories that, while incredibly successful in their own domains, have proven difficult to merge into a single theory of quantum gravity. If light were to fluctuate in extreme conditions, it would imply that the speed of light is not truly constant under all circumstances, but rather that it could change depending on the state of the environment. While this idea has yet to gain widespread acceptance, it's an intriguing reminder that the universe is far more complex than we often imagine. What we know about light speed might only be valid under typical everyday conditions, those that don't stretch the fabric of space-time too much, or those that don't involve the extremes of black holes or the early moments of the Big Bang. If Schwindt's theories are proven true, we would have to reconsider our definition of the speed of light, which would have profound implications for everything from our understanding of distant galaxies to the way we study subatomic particles. At the same time, Lee Smolin, a theoretical physicist known for his work on loop quantum gravity, has also questioned the constancy of the speed of light, but in a different way. Smolin proposes that light speed might not be a fixed universal constant, but instead could vary depending on the curvature of spacetime. This idea is rooted in his broader theory of loop quantum gravity, which suggests that spacetime itself is quantized, made up of tiny discrete chunks, rather than being a smooth, continuous fabric. In Smolin's view, the structure of spacetime might influence the behavior of light in ways we haven't yet fully explored. If Smolin's ideas are correct, the speed of light would not be a strict constant, but rather something that could change based on the underlying fabric of spacetime itself. The consequences of this would be enormous. It would mean that the way we measure distance, time, and mass would need to be reconsidered, because the relationship between space and time might not be as fixed as we currently believe. Theories such as Smolin's also open the door for new ways of looking at the universe's evolution, from its birth in the Big Bang to its eventual fate. If the speed of light could vary, even in small amounts, it could provide a clue about how the universe has changed over time, or how it might evolve in the future. Yet another provocative challenge to the constancy of light's speed comes from the work of Julian Barbour, a British physicist who has developed a theory of timelessness. Barbour's work is deeply philosophical, as it challenges the very nature of time itself. According to Barbour, time does not flow in a continuous linear manner. Instead, he suggests that the universe consists of a series of nows, individual discrete moments that exist without a past or future. In this view, the flow of time is an illusion, and our perception of the passage of time is merely a construct of our consciousness. Barbour's theory has fascinating implications for the speed of light. If time itself is not continuous but rather a series of moments, then the idea of light moving through time as we currently understand it might be fundamentally flawed. According to Barbour, light, and indeed all physical phenomena, might emerge from this timelessness, rather than travelling through time as we traditionally think of it. In essence, light could be seen as an emergent property of the universe, a result of the interaction between these discrete nows that make up our reality. Barbour's ideas challenge our most basic intuitions about the nature of time, space, and light. If time is an illusion, and if light is something that emerges from a timeless existence, then the constancy of light's speed might be far less absolute than we have assumed. In a universe without a flowing time, the very concept of speed may need to be redefined. Instead of measuring how fast light travels through time, we might have to think about how light emerges in relation to the fabric of the universe itself. Barbour's theory doesn't just challenge the speed of light, it challenges the entire framework within which we measure anything, from the movement of stars to the ticking of clocks. These diverse ideas, from Schwindt's potential fluctuations in light speed under extreme conditions, to Smolin's space-time curvature theory and Barbour's timelessness, offer intriguing possibilities that could change how we understand the nature of light itself. They remind us that science is not a final destination, but an ongoing journey, one where even the most established truths can be questioned and reconsidered. But despite these challenges, the speed of light remains an essential part of our physical laws. It is the constant that governs so much of our universe, from the way we measure distances in space to the fundamental laws of relativity. The constancy of light speed allows us to define time and space in a way that is both practical and consistent with the way we observe the universe. Without this constant, the equations that underpin so much of modern physics would fall apart, and our understanding of the cosmos would be incomplete. Perhaps then, the speed of light is not just a simple constant, but a cornerstone of our understanding of reality itself. Even as theories emerge that challenge this idea, it's clear that light's speed plays a crucial role in how we perceive the universe and the laws that govern it. Whether we're observing distant stars, measuring the curvature of spacetime, or trying to unlock the deepest secrets of quantum mechanics, the speed of light remains a central player in the cosmic dance, a constant that shapes the very fabric of the universe. One of the most striking predictions of Einstein's general theory of relativity was the idea that massive objects could bend the fabric of space and time itself. This was a radical departure from the previous Newtonian understanding, where gravity was seen as a force acting at a distance. But Einstein's theory suggested something much deeper. He proposed that mass and energy actually curve space-time around them, and this curvature, in turn, affects the path of objects moving through space, including light. The bending of light by gravity, now known as gravitational lensing, was something that Einstein predicted in 1905. The theory suggests that light, which travels in straight lines under normal circumstances, would follow curved paths when it passes near a massive object. This phenomenon occurs because the space-time around that object is distorted, pulling the light towards it. Just as a lens bends light in a way that magnifies or distorts an image, a massive object like a star or galaxy can bend light from a distant source, creating optical effects that allow us to see objects behind the massive body, even though they would otherwise be hidden from view. Gravitational lensing was a purely theoretical prediction until 1932, when Arthur Eddington and his team confirmed it during a solar eclipse. Eddington measured the bending of starlight around the Sun, and his observations were in line with Einstein's predictions. This discovery was one of the first direct pieces of evidence supporting general relativity, and was a major turning point in our understanding of gravity. Since then, gravitational lensing has become an important tool in astronomy, helping scientists study distant galaxies, black holes, and even the elusive dark matter that makes up much of the universe's mass. As we move to more extreme environments, the effects of gravitational lensing become even more pronounced. One of the most fascinating and mysterious objects in the universe that bends light in dramatic ways is the black hole. A black hole is a region of space where the curvature of space-time is so intense that not even light can escape from it, making it invisible to direct observation. The boundary of a black hole, known as the event horizon, marks the point beyond which nothing can escape. The British physicist Roger Penrose was a key figure in understanding the nature of black holes and their interaction with light. Penrose developed important ideas about the structure of black holes, especially around the concept of singularities. A singularity is a point at the centre of a black hole where the curvature of space-time becomes infinite and all the matter within the black hole is concentrated in a space of zero volume. At this point, the known laws of physics break down. Penrose's work showed that when matter falls into a black hole, it is crushed to this point of infinite density, and the gravitational forces become so strong that they warp space-time in ways that we can hardly imagine. Light behaves very differently near a black hole, as the intense curvature of space-time has a dramatic effect on its path. As light approaches a black hole, it gets stretched and distorted, a process known as gravitational redshift. This means that the light's wavelength gets longer, shifting it towards the red end of the spectrum. If the light gets too close, beyond a certain critical point known as the photon sphere, it can even become trapped in orbit around the black hole. This is one of the reasons why black holes are so difficult to study directly. Any light that enters the event horizon can never escape, and so we cannot observe the black hole itself. Instead, we study the effects that the black hole has on the space and matter around it. Kip Thorne, a theoretical physicist known for his work on black holes and gravitational waves, made important contributions to our understanding of how light behaves around rotating black holes, also known as Kerr black holes. Thorne's work on the effects of rotation on a black hole's spacetime was groundbreaking. He demonstrated that when a black hole spins, it not only affects the path of light, but also distorts the space around it in a way that creates phenomena like frame dragging. This effect occurs when the rotating black hole drags the surrounding spacetime with it, causing light that passes nearby to be pulled along in the same direction. The consequences of this frame dragging are dramatic. Light, which would normally travel in straight lines, gets twisted and distorted as it moves through this warped space-time. This can cause light to follow an unexpected path, making it possible for scientists to observe effects that would otherwise be invisible. The study of rotating black holes and their interaction with light has provided critical insights into the nature of gravity, space-time, and the extreme environments near these cosmic objects. While black holes are among the most extreme examples of gravitational lensing, they are far from the only places where light's path can be bent. In fact, gravitational lensing occurs all across the universe, wherever there is mass. This includes galaxies, clusters of galaxies, and even large-scale structures like the cosmic web. The bending of light allows astronomers to observe distant objects that would otherwise be hidden from view. For example, light from galaxies that are billions of light-years away can be bent by a closer galaxy, or galaxy cluster, acting like a giant magnifying glass, bringing those distant galaxies into view. Gravitational lensing has become one of the most powerful tools in modern astronomy. It helps scientists map out the distribution of dark matter, which does not emit or reflect light and is invisible to most traditional observation methods. By studying how light bends as it passes through galaxy clusters, scientists can measure the amount of dark matter in those clusters, providing valuable insights into one of the most mysterious components of the universe. The study of gravitational lensing also opens the door to understanding the large-scale structure of the universe. Light from distant objects can provide us with clues about the history and evolution of the cosmos. The bending of light acts as a cosmic fingerprint, allowing us to trace the path of photons as they journey through time and space. In this way, gravitational lensing becomes a tool for looking not just at the universe's present state, but also at its past, offering a glimpse into how galaxies and stars formed, evolved, and interacted over billions of years. Gravitational lensing is a reminder of the profound influence that space-time has on light, and, by extension, on our understanding of the universe. Whether it's the bending of light around a distant galaxy, or the warping of space-time near a rotating black hole, the study of how light interacts with gravity continues to push the boundaries of our knowledge. The effects of gravitational lensing are not just theoretical curiosities, they're a window into the very fabric of the cosmos, providing us with clues about the invisible forces that shape the universe on the grandest scales. Through the lens of light, we can peer deeper into the mysteries of space-time, unveiling secrets that would otherwise remain hidden in the vast darkness of the cosmos. When light travels through different materials, its speed changes, slowing down as it passes through substances denser than a vacuum. This behavior is known as refraction, and it's a phenomenon that can be easily observed when light bends as it enters water or glass from air. But why does this happen? The answer lies in the interaction between light and the atoms or molecules of the material. To understand this, we look to the work of physicists like Arnold Sommerfeld and Max Born, who made important contributions to our understanding of light's refractive properties in the early 20th century. Sommerfeld, a German physicist, developed a more detailed mathematical framework for understanding how light interacts with materials at the atomic level. His work helped to explain the changes in light's speed when it passes through different media, laying the groundwork for modern theories of electromagnetic waves. Born, another German physicist, furthered Sommerfeld's work by analysing light in a more quantum mechanical way. He used ideas from quantum mechanics to describe how light interacts with the electrons in materials. Born's theory showed that light's behaviour, especially its speed, could be understood in terms of how the electromagnetic waves of light were absorbed and re-emitted by the atoms in the material. This process caused the light to slow down, as the energy from the light was temporarily absorbed by the material before being re-emitted. The extent of this slowing down depends on the material's refractive index, a value that describes how much the material bends light compared to a vacuum. The refractive index of a material is crucial in determining how light behaves when it passes through it. For example, the refractive index of air is approximately 1, meaning light travels through air at nearly its maximum speed. Water has a refractive index of about 1.33, meaning light travels through it about 1/3 slower than in a vacuum. Glass, depending on its type, can have a refractive index ranging from 1.5 to 1.9, further slowing down light. But light is not just a simple wave moving through a material, it also behaves like a particle. This wave-particle duality, first proposed by Louis de Broglie in 1924, introduced the idea that light can exhibit both wave-like and particle-like properties depending on how we observe it. According to de Broglie, light, or any other particle, can be thought of as a wave with a specific wavelength and frequency. This wave-particle duality became central to our understanding of light's behavior, particularly in how it interacts with matter. In materials, the wave nature of light is more apparent when we look at phenomena like interference and diffraction, where light waves overlap and either reinforce or cancel each other out. But at the same time, the particle nature of light, embodied in photons, becomes apparent in processes like the photoelectric effect, where light can knock electrons off atoms. De Broglie's insights into the wave-particle duality opened up new ways of thinking about how light interacts with matter at the quantum level. When light enters a new material, it can be thought of as a wave that spreads out and slows down as it interacts with the atomic structure of the material. But it can also be treated as a stream of particles that transfer energy to the electrons in the material. This duality is particularly important when we think about light speed in different materials. In a vacuum, light travels at its maximum speed, but in materials it interacts with the particles in the material and slows down. However, when we take into account both the wave and particle nature of light, we see that the light's behavior in a material is influenced by how its waves interact with the atoms, as well as how its individual photons transfer energy to those atoms. To gain further insight into light's behavior at different speeds, we turn to the path integral approach developed by Richard Feynman, one of the most influential physicists of the 20th century. Feynman's path integral formulation provides a way of understanding the motion of particles, including light, by considering all possible paths that the particle could take. Instead of looking at a single trajectory, Feynman's approach calculates the probability of a particle following any given path, and then sums up all the possibilities to determine the most likely behavior. This approach has important implications for understanding light's speed in different materials. According to Feynman, light doesn't just take one straight path through a material, it takes many different paths, some of which are longer or shorter than others. The speed of light in a material is determined by the sum of all these different paths, with the most likely path being the one that corresponds to the light's behavior in that material. This idea helps explain how light can travel at different speeds in different materials, as the nature of the material determines the paths the light can take, and how those paths are affected by the material's atomic structure. Feynman's work on path integrals also introduced a more fundamental understanding of light's interaction with materials at the quantum level. By considering all possible pairs that light could take, Feynman's approach highlights the complexity of light's behavior, especially in materials with different properties. The idea that light doesn't just travel in one straightforward direction, but explores multiple paths offers a more nuanced view of how light's speed changes in different contexts. It's important to remember that when light travels through a material, its speed is determined by how the light interacts with the atoms and molecules that make up the material. These interactions depend on the refractive index of the material, which varies depending on the type of material, but light's behavior is also influenced by the material's quantum properties, as Feynman's path integral formulation suggests. Together, these factors shape how light slows down or speeds up when it passes through different substances. Understanding light's speed in different media is not just about studying the material itself, it's about understanding the complex interplay between light's wave and particle nature, the atomic structure of the material, and the quantum processes that govern both. Whether we're looking at the light traveling through water, glass, or even more exotic materials like semiconductor crystals, the principles of refraction, wave-particle duality, and quantum mechanics all come into play. This deeper understanding allows us to apply light in a wide range of technologies, from fiber optics to lasers, and helps us explain how light behaves in the natural world, from the bending of light in rainbows to the creation of colors in materials. In the end, the speed of light is not just a simple number, but a window into the fascinating and complex interactions that govern the universe at both macroscopic and microscopic scales. As we continue to study light in different materials, we uncover more about the fundamental nature of reality itself. For centuries, light was thought to be purely a wave, a continuous disturbance that propagated through space. But at the dawn of the 20th century, this classical understanding was completely upended. The first major hint that light might behave differently came from Max Planck, a German physicist, in 1901. Planck was studying the radiation emitted by heated objects, a problem that had puzzled scientists for some time. Classical physics could not explain why objects like metal bars glowed when heated, and why their colour shifted from red to blue as they got hotter. Planck's insight was simple yet revolutionary. He proposed that energy was not emitted in a continuous manner but in discrete packets, which he called quanta. This idea of quantized energy was a departure from the smooth, continuous wave theory of light that had prevailed for so long. But it wasn't until Albert Einstein took Planck's work further in 1905 that the true implications of this idea for light itself began to unfold. Einstein applied Planck's concept of quantized energy to explain the photoelectric effect, an experimental observation where light striking a metal surface could cause it to emit electrons. Classical wave theory could not explain this effect. After all, if light was a continuous wave, then its energy would gradually build up to knock electrons loose. But Einstein argued that light also behaves like particles, specifically tiny packets of energy called photons. These photons had specific energy levels, and when the energy of a photon was high enough, it could knock an electron loose from the metal. This was a pivotal moment in the development of quantum mechanics, showing that light could behave both as a wave and as a particle. This duality would become a cornerstone of modern physics, fundamentally altering our understanding of the universe. The implications of Einstein's work on the nature of light were profound. The idea that light could exhibit both wave-like and particle-like properties opened up a new realm of possibilities for how we understood the universe. But it wasn't just light that was affected. Quantum mechanics, the theory that arose to explain these strange behaviors, challenged many classical concepts in physics, from the way we understood particles and waves to our conception of time and space. One of the most important developments in quantum mechanics came from Werner Heisenberg, a German physicist who, in 1927, introduced his uncertainty principle. Heisenberg's principle stated that it is impossible to simultaneously know both the position and the momentum of a particle with absolute certainty. The more precisely we measure one of these properties, the less precisely we can know the other. This idea was groundbreaking because it suggested that, at a fundamental level, nature itself was inherently probabilistic. Unlike classical physics, where particles could be pinpointed and predicted with certainty, quantum mechanics showed us that we could only know the probabilities of where a particle might be or how fast it might be moving. Heisenberg's uncertainty principle had a major impact on our understanding of light. For instance, it meant that light could not be treated as a simple, predictable wave traveling through space. Rather, the behavior of light was subject to quantum uncertainty. Its position and momentum could not be fully determined at the same time. This concept was unsettling for many scientists, as it contradicted the deterministic worldview that had been established by Newtonian mechanics. But it was also a profound realization that challenged our understanding of the very nature of reality. The uncertainty principle also led to a deeper exploration of how light interacted with the smallest particles in the universe. As light interacts with matter, it is no longer simply a predictable wave or particle. Instead, it's governed by the complex interplay of quantum probabilities, where each interaction could lead to a range of possible outcomes. This realization opened the door to a more nuanced understanding of light and its behavior, one that would continue to evolve throughout the 20th century. As quantum mechanics developed, the implications for the speed of light became increasingly intriguing. In 1964, John Bell, a physicist from Northern Ireland, made a significant contribution to our understanding of quantum phenomena with Bell's theorem. Bell showed that quantum mechanics predicted correlations between particles that could not be explained by classical physics. This was especially important in the context of quantum entanglement, a phenomenon where particles become linked in such a way that their properties are instantaneously correlated, even if they are separated by vast distances. This instant connection between entangled particles seemed to challenge the idea that information could only travel at the speed of light. Bell's work suggested that the quantum world was far more interconnected and complex than anything classical physics had imagined. If particles could be entangled in such a way that changes to one particle could affect the other instantly, then the idea of a universal speed limit set by the speed of light was called into question. While quantum entanglement doesn't violate the speed of light directly, no information is actually transmitted faster than light. It suggests that there may be deeper, more mysterious connections between particles that transcend the limits we place on our understanding of the universe. These ideas led to further debates about the role of light in quantum mechanics. Could the speed of light really be the ultimate limit, or was it just another concept in the classical framework that was being slowly deconstructed by quantum theory? Could quantum entanglement, for instance, imply that there are connections in the universe that are beyond the reach of light, at least in the traditional sense? These questions have led to some of the most fascinating and speculative ideas in modern physics, from theories of wormholes and faster-than-light travel to the concept of a multiverse, where different versions of reality could be connected in ways that defy our understanding of space and time. At the heart of these ideas lies the continued tension between the wave and particle natures of light. On one hand, light behaves like a wave, spreading out and interacting with matter in a way that can be predicted and modelled. On the other hand, it also behaves like a particle, with discrete packets of energy that interact with individual atoms and electrons. This duality, first proposed by Louis de Broglie in 1924, lies at the foundation of quantum mechanics, shaping the way we understand everything from the behavior of light to the structure of the universe itself. As our understanding of light deepens, we come to appreciate the ways in which it challenges our most fundamental assumptions about the universe. Light in all its complexity continues to be both a mystery and a tool, mysterious in its quantum behavior but also a powerful key to unlocking the deeper workings of reality. The more we learn about light, the more we realize how much we have yet to discover, and how the very nature of light might hold the answers to some of the greatest questions in physics. Light plays a crucial role in how we perceive the universe, not just by illuminating the world around us, but by providing a window into the farthest reaches of space and time. The speed of light helps define the limits of our observable universe, setting the boundary of what we can see, and it is intimately connected to the cosmic expansion that has been unfolding since the beginning of time. To understand this, we need to look back to the early 20th century, when Georges Lemaitre, a Belgian priest and physicist, made a groundbreaking observation. Lemaitre proposed that the universe was not static, but rather expanding from a single, incredibly dense point in the past. His idea was that the galaxies we see today are all moving away from us, and the farther away a galaxy is, the faster it appears to be receding. This was a bold suggestion, and it set the stage for one of the most profound discoveries in cosmology: the expansion of the universe. This concept of an expanding universe was confirmed by Edwin Hubble in 1929. Hubble observed that light from distant galaxies was redshifted, meaning its wavelength had stretched as the galaxies moved farther away from us. This redshift occurs because, as the universe expands, the space between objects also expands, stretching the light travelling through it. The faster a galaxy moves away, the more its light is stretched, and the more redshifted it becomes. The relationship between distance and velocity, known as Hubble's law, showed that the universe was indeed expanding in a way that supported Lemaitre's earlier hypothesis. The speed of light, in this context, becomes a fundamental measuring stick for understanding the scale of the universe and the rate at which it is expanding. As we consider the vast distances involved, light from distant galaxies can take billions of years to reach us. It's important to realize that the speed of light sets an upper limit on how far we can see and how much we can learn about the past. When we look at the light from faraway galaxies, we're not just seeing them as they are today, but as they were when that light first left them, often billions of years ago. The farther away a galaxy is, the older the light we see, and the further back in time we can peer. But while Hubble's observations confirm the expansion of the universe, they also raise new questions. If the universe is expanding, what is causing it to speed up, and what is driving this expansion? In 1998, scientists made a surprising discovery. Two independent teams of astronomers, led by Saul Perlmutter, Brian P. Schmidt, and Adam G. Rees, observed that not only was the universe expanding, but the expansion was accelerating. This acceleration, they found, was due to a mysterious force they called dark energy. Dark energy is thought to make up about 70% of the universe's total energy content, yet it remains one of the most enigmatic components of the cosmos. Its existence is inferred from the way galaxies are moving apart, but it has never been directly observed. Dark energy appears to counteract gravity, pushing the universe to expand at an ever-increasing rate. This discovery reshaped our understanding of the cosmos, and it had profound implications for the future of the universe. If the acceleration continues, it could lead to a future where galaxies are so far apart that light from distant objects would no longer be able to reach us, isolating us from the rest of the universe. The connection between the speed of light and the expansion of the universe is also crucial in understanding cosmological models, especially when we consider the role of light in measuring distances. The cosmic light horizon, which is the furthest distance from which light has had time to reach us since the beginning of the universe, defines the observable universe. As the universe expands, the light from far-off galaxies becomes stretched, and its speed relative to the expanding space appears slower from our point of view. This is another place where the speed of light intersects with the fabric of space-time, showing us how even light itself is affected by the overall expansion of the universe. Michael Turner, a prominent cosmologist, has contributed significantly to the understanding of dark energy and its role in the universe's expansion. Turner's work on cosmological models has helped scientists incorporate dark energy into our understanding of the universe's fate. He's explored how the energy from dark energy interacts with the speed of light in models of cosmic inflation, a period of rapid expansion in the early universe. During this phase, space itself expanded at a pace far faster than the speed of light, creating the large-scale structure of the universe that we observe today. Turner's insights help us reconcile the speed of light with the ongoing expansion of the universe and the forces that shape it. As we observe the universe, we must also consider the limitations imposed by the speed of light. The farther away an object is, the older the light we observe. In practical terms, this means that we are looking into the past every time we observe a distant galaxy. The speed of light thus sets a boundary not just in space, but also in time. The farther out we look, the further back we are peering into the universe's history, seeing galaxies as they were billions of years ago. This is why observations of distant objects are so valuable. They allow us to study the early universe, learning about its formation, evolution, and the forces that have shaped it. Yet the speed of light also tells us something profound about the ultimate fate of the universe. As the universe expands and dark energy continues to push galaxies apart, there will come a time when the light from distant galaxies will no longer reach us. The expansion will cause galaxies to recede from each other at a speed faster than that of light, meaning their light will never reach us. The cosmic event horizon is the point beyond which we can no longer see any objects, no matter how powerful our telescopes become. The speed of light, then, plays a critical role in defining the boundaries of both the observable universe and our understanding of its future. It shapes how we explore the cosmos, how we interpret the light from distant galaxies, and how we model the expansion of space itself. As we look out into the universe, we are not just observing the stars and galaxies, but also the unfolding of time and the evolution of the cosmos. Every ray of light, every shift in the redshift, every glimpse of the farthest reaches of space brings us closer to understanding how the universe came to be and where it is headed. The speed of light, in all its constancy, helps define the limits of our knowledge and our place in the vast expanse of the cosmos. It is a constant that governs not only the flow of information across the universe, but also our ability to understand the very fabric of space-time. Whether we are studying the distant galaxies that populate the outer reaches of the observable universe or the effects of dark energy on cosmic expansion, the speed of light remains a crucial factor in our exploration of the universe's history, structure, and future. Time travel is one of those concepts that has fascinated humanity for centuries, and it has captured our imagination in countless books, movies, and scientific discussions. The idea of moving through time, whether travelling into the past or the future, seems almost like something out of science fiction. However, when we look at the nature of space, time, and light, we begin to see that time travel isn't as far-fetched as it might first appear, though it's far more complex than we might have expected. One of the first scientists to seriously consider the possibility of time travel was Albert Einstein. His special theory of relativity, and later his general theory of relativity, changed our understanding of time from being a rigid, absolute concept to something far more flexible, depending on the observer's relative motion and the curvature of space-time. Einstein showed that time could slow down or speed up depending on the speed at which an object is moving, or how close it is to a massive object like a planet or star. This phenomenon is known as time dilation, and it has been experimentally verified in numerous ways, such as with atomic clocks flown around the world in airplanes. While this doesn't allow for traditional time travel, it does show that time can be affected by speed and gravity in ways that make it less absolute than we once thought. Building on Einstein's work, Kurt Gödel, a German mathematician and logician, introduced a fascinating theory in 1949 that suggested time travel could be possible within the framework of general relativity. Gödel proposed that the universe could have a rotating structure, meaning that space-time itself could rotate in such a way that it loops back on itself. In a universe like this, it would be possible to travel along a path that could bring you back to your starting point in both space and time. This is what we call a closed time-like curve, CTC, and it would allow for the possibility of time loops, where you could travel back to a moment in the past. Gödel's rotating universe model, however, requires very specific conditions that we do not observe in our own universe. His theory was more of a mathematical curiosity than a practical blueprint for time travel, but it opened the door to the idea that, at least within the realm of relativity, time loops might be possible. While Gödel's rotating universe introduced the idea of closed time-like curves, another physicist, Miguel Alcubierre, took the concept further by proposing a way to bypass the speed of light, opening the door to faster-than-light travel and potentially time travel. In 1994, Alcubierre introduced the concept of the warp drive, a theoretical mechanism that could allow a spacecraft to travel faster than light without violating the laws of relativity. The warp drive doesn't actually move a spacecraft faster than light in the traditional sense. Instead, it distorts space-time itself. Imagine space-time like a fabric. The warp drive would contract space in front of the spacecraft and expand space behind it. In this way, the spacecraft would remain stationary within its own local space-time bubble, while the space around it moves, effectively allowing it to travel faster than light without breaking any rules. Alcubierre's warp drive idea is based on the principles of general relativity, and while it remains purely theoretical, it has captured the attention of scientists and engineers alike. The fascinating thing about this concept is that it doesn't require any exotic particles or new forms of matter. It simply relies on manipulating space-time itself. However, there's a catch. To make a warp drive work as Alcubierre envisioned it, we would need vast amounts of energy, far more than we can currently produce. There's also the issue of how such a craft might interact with the rest of the universe, as it moves faster than light, and whether or not this could cause catastrophic side effects. While the warp drive is a fascinating idea, it remains firmly in the realm of speculative physics. Even if we can imagine bending space-time to make time travel possible, we still have to consider how light behaves in these extreme situations. The speed of light is a constant in the equations of relativity, and it sets a strict upper limit on how fast information and matter can travel. But in theories like Alcubierre's warp drive, the fabric of space-time itself is what is being manipulated, not the objects or information within it. This is crucial because it means that even if we could theoretically exceed the speed of light in a local bubble of space-time, we wouldn't be violating the fundamental principles of relativity. Instead, we would be shifting the space around us in a way that allows us to travel vast distances, or even back in time, without ever exceeding the speed limit set by the universe. Another concept closely related to time travel comes from John Wheeler, an American theoretical physicist who made significant contributions to the study of black holes and the structure of space-time. Wheeler is famous for his work on wormholes, which are theoretical passages through space-time that could connect distant parts of the universe, or even different points in time. Wormholes are often depicted in science fiction as shortcuts for faster-than-light travel, but they are also grounded in real physics. In general relativity, a wormhole could be imagined as a tunnel with two ends, each located in a different part of space-time. If such a structure existed, it might allow an object to travel from one point to another instantaneously, bypassing the distance in between. If one end of a wormhole were to move at a significant fraction of the speed of light, this could create a time difference between the two ends of the wormhole, making it possible to travel back in time by entering the wormhole at one end and exiting it at the other. However, just like the warp drive, wormholes remain entirely theoretical, and no experimental evidence has been found to support their existence. Even if they were possible, there are numerous challenges. For instance, a wormhole would require some form of exotic matter with negative energy to keep it open, as the gravitational forces of the black holes at the ends of the wormhole would otherwise cause it to collapse. Moreover, the effects of travelling through a wormhole are not entirely clear. Would light and other forms of matter behave the same way inside? Could we manipulate the structure of space-time in a controlled way? Or would entering a wormhole result in catastrophic consequences? Despite these challenges, the idea of wormholes, along with Alcubierre's warp drive and Gödel's time loops, points to a deeper question about the nature of time and space. Theories about time travel are not just about travelling to the past or future. They're about understanding the very fabric of space-time itself and how it might be manipulated. The speed of light in this context isn't just a limit on how fast we can move, it's a clue about the deeper structure of the universe, one that we're still trying to unravel. Time travel may seem like a concept for science fiction, but the questions it raises touch on some of the most fundamental aspects of physics. From the nature of light speed to the structure of space-time itself, the theories about time travel challenge our understanding of the universe and point to new possibilities for the future. While we may not yet be able to travel through time, the exploration of these ideas opens the door to new ways of thinking about the universe, its past and its future. The speed of light is a fundamental limit in the universe, but what if there were particles that could break this limit? For decades, the idea of superluminal particles, particles that travel faster than light, has intrigued physicists and captured the imagination of science fiction writers alike. The most famous of these hypothetical particles are called tachyons, a term first coined by the physicist Gerard 't Hooft in 1967. Tachyons are particles that, according to certain equations in special relativity, would always travel faster than light. In theory, these particles could exist in the realms of quantum mechanics, though no experimental evidence has ever confirmed their existence. According to special relativity, as an object with mass approaches the speed of light, its energy increases without bound, meaning it would require infinite energy to actually reach the speed of light. But tachyons, by definition, would have imaginary mass, meaning they would behave in ways that are fundamentally different from the particles we experience in our everyday world. If tachyons could exist, they might not only violate the speed of light limit, but could also create bizarre effects, such as moving backward in time depending on how they interact with space-time. While tachyons remain a speculative concept, they represent a fascinating challenge to our understanding of the universe. If such particles existed, they could offer a window into physics beyond the standard model, and might even provide insights into how we could bypass the speed of light or explore phenomena that defy our traditional conception of causality and time. However, there are a number of unresolved questions surrounding tachyons. For instance, if they were travelling faster than light, how would they interact with slower than light particles? Would their existence be consistent with the known laws of physics, or would it necessitate a complete reworking of how we understand the fabric of space-time? While tachyons are a tantalizing possibility, they are not the only theoretical challenge to the idea of the speed of light as an absolute limit. In fact, there are theories that don't just allow for faster-than-light particles, but suggest that our entire understanding of time and space may need to be reimagined. One such theory comes from the work of Erich Jantsch, an Austrian physicist who proposed a radical idea about time itself. In his theory of nonlinear time, Jantsch challenged the very foundation of our understanding of light's role in the universe. In classical physics, time is treated as linear, a constant, unchanging progression from past to present to future. But Jantsch's nonlinear time theory suggests that time doesn't flow in a continuous, predictable way. Instead, he proposed that time itself might be more like a network of interconnected moments that don't follow a strict sequence. In this view, events are not simply laid out in an ordered timeline, but rather exist as points that can be connected in multiple, nonlinear ways. This concept challenges the very foundation of how we think about light's speed, because in a universe governed by nonlinear time, the behavior of light could vary drastically depending on how time itself is perceived. If time is nonlinear, then the notion of a single fixed speed of light might break down. Light's speed, in such a scenario, could be fluid, changing depending on how space-time is structured at any given moment. This opens the door to new theories of relativity that go beyond the well-established model, potentially allowing for faster-than-light travel, time loops, or even time travel, depending on the precise structure of space-time. Jantsch's work adds to a growing body of ideas that challenge the classical view of light and its speed, offering an alternative perspective where the very concept of time, and by extension, light, might behave in unexpected and non-traditional ways. These ideas dovetail with the work of John Archibald Wheeler, a celebrated physicist who is known for his work on black holes and the concept of quantum foam. Wheeler's work was instrumental in developing our understanding of the quantum nature of space-time, particularly the idea that space and time are not continuous but are composed of discrete quantum units. This view suggests that space-time itself may be foamy at the smallest scales, and this foam-like structure could have profound implications for how light behaves in such an environment. In Wheeler's vision, space-time is not a smooth, uninterrupted fabric, but a dynamic and fluctuating entity at the quantum level. The concept of quantum foam challenges the classical understanding of space-time as a stable backdrop against which events unfold. Instead, at extremely small scales, space-time might be subject to wild fluctuations, creating a sort of froth of uncertainty. This quantum foam could affect how light interacts with space itself, possibly allowing for phenomena that break the traditional limits of light speed. For example, if space-time is not smooth and continuous, the rules that govern light speed might no longer apply in the same way we've come to expect. One possible implication of quantum foam is that light could travel at different speeds depending on the texture of the space it moves through. This could mean that light speed is not a universal constant, but a variable quantity that depends on the structure of space-time at any given location. In regions where space-time is particularly foamy, light might behave differently than in more stable regions, potentially allowing for faster-than-light travel or other exotic effects. While the idea of quantum foam, and the potential for light to behave differently in such environments remain speculative. It's an exciting possibility that challenges our assumptions about the universe. Wheeler's work on quantum gravity, along with his exploration of spacetime's microscopic structure, suggests that there is still much to learn about the fundamental nature of light. The idea that light speed could vary depending on the properties of spacetime at the quantum level opens up new frontiers in our understanding of physics, pushing us to reconsider what we think we know about the universe and the limits of light. These theories, tachyons, nonlinear time, and quantum foam, suggest that the speed of light, while still a crucial factor in our understanding of the universe, may not be as absolute as we once believed. As physicists continue to probe the deepest mysteries of space and time, it's possible that the speed of light will be revealed to be more flexible and dynamic than we've imagined. Whether through faster-than-light particles, shifts in the fabric of spacetime, or the very nature of time itself, the future of physics may hold surprises that challenge our current conception of light's role in the cosmos. It's a reminder that in science, the more we learn, the more questions arise, and the universe continues to reveal its secrets in ways that continue to astonish and inspire. In our understanding of the universe, one of the most enduring and fundamental concepts is the speed of light. It's the universal speed limit, governing how fast anything can travel through space and shaping the very structure of our reality. However, as we move deeper into the realms of modern physics, especially with the advent of quantum mechanics and general relativity, the relationship between light and spacetime becomes more complex, opening the door for new theories that could potentially modify the way we think about light speed. One of the most promising areas of research in this field is quantum gravity, a theoretical framework attempting to unify quantum mechanics and general relativity, the two pillars of modern physics that, up until now, have not fully coexisted. One approach to quantum gravity is loop quantum gravity, LQG, a theory that proposes that space-time is not a smooth continuum, but instead made up of discrete, quantized units. This idea suggests that the very fabric of space-time might behave differently at the smaller scales, particularly at the Planck scale, where both quantum mechanics and gravitational effects are significant. In this context, the speed of light could be affected by the quantum properties of space-time. Instead of the smooth, continuous space-time we're used to, loop quantum gravity suggests that space-time might be granular, with tiny chunks of space-time influencing how light travels through it. Lee Smolin and Carlo Rovelli, two of the leading researchers in this area, have made significant contributions to the development of LQG. Smolin, in particular, has explored the potential implications of this theory on our understanding of space, time, and light. In a quantum gravitational framework, light could behave in unexpected ways. Its speed might vary depending on the interaction between light and the quantum structure of spacetime itself. For instance, at the smaller scales, light might experience a form of friction as it interacts with the granular structure of space, causing it to slow down. This could have profound implications for our understanding of the speed of light, suggesting that it might not always be constant, particularly in regions of extremely high gravity or in the early universe, where quantum gravitational effects are likely to be most pronounced. Carlo Rovelli, another key figure in LQG, has contributed to the theory's development by proposing that the structure of spacetime itself is fundamentally tied to the quantum properties of matter. Rovelli's work suggests that the speed of light might not be a fixed quantity in the way we've traditionally understood it. Instead, the behavior of a light could change in ways we've yet to fully grasp, depending on the underlying quantum structure of the universe. This might lead to a new understanding of how light interacts with spacetime at the most fundamental levels, potentially opening the door to new forms of travel or information transfer that were previously thought to be impossible. The idea that the speed of light could change under quantum conditions is not the only one being explored by physicists today. Nima Arkani-Hamed, a prominent theoretical physicist, has also proposed an entirely different approach to understanding spacetime and the speed of light, one that involves higher dimensional space. Arkani-Hamed's research focuses on the concept of extra dimensions, which go beyond the 3 dimensions of space and 1 dimension of time that we're familiar with. According to certain theories in high-energy physics, there may be additional spatial dimensions that are hidden from our everyday perception, dimensions that could have significant effects on the behavior of light and space-time. In these higher dimensional models, such as string theory or M-theory, The laws of physics as we know them might not apply in the same way. These theories suggest that the properties of light, including its speed, could be influenced by the geometry of these extra dimensions. For instance, in some higher dimensional models, spacetime itself could be curved in ways that are invisible to us in the familiar three-dimensional world, but have a profound impact on how light behaves. The speed of light might appear to vary depending on the curvature of these extra dimensions, and light might be able to access these hidden dimensions in ways that we cannot yet measure. Arkani Hamed's work suggests that our current understanding of the speed of light based on a four-dimensional universe might be incomplete. If there are higher dimensions that we cannot directly observe, these dimensions could influence the propagation of light in ways that are not accounted for in classical physics or even in our current understanding of quantum mechanics. This could offer new ways to think about the speed of light, not as an unchanging constant, but as something that could be influenced by the deeper structure of the universe itself. The relationship between light and spacetime becomes even more intriguing when we consider how these new theories could challenge the very foundations of causality and relativity. In classical physics, the speed of light serves as the ultimate speed limit, governing the transfer of information and defining the structure of spacetime. But if the speed of light can vary, either because of the quantum structure of spacetime, the influence of higher dimensions, or other unknown factors, it could fundamentally change our understanding of time, causality, and the very fabric of the universe. For instance, if light's speed could be altered in certain conditions, this might lead to situations where information could be transmitted faster than light, potentially allowing for communication or even travel across vast distances without violating the principles of relativity. This raises fascinating questions about the nature of causality. In classical physics, causality, where cause precedes effect, is a cornerstone of how we understand the universe. But if the speed of light is not constant or could be manipulated, it could lead to scenarios where the order of events is no longer so easily defined, creating paradoxes that challenge our understanding of time and space. These ideas are still very much in the realm of theoretical physics, and there's much we don't know about how quantum gravity and higher dimensional space might affect the behavior of light. However, the work of Smolin, Rovelli, Arkani Hamed, and others provides tantalizing glimpses into a future where our understanding of the speed of light and spacetime could be far more complex and more flexible than we've ever imagined. The prospect that light's speed could vary depending on quantum conditions, or that higher dimensional physics could offer new insights into its behavior, opens up a whole new chapter in our exploration of the universe. Ultimately, the questions raised by these theories suggest that our current understanding of the speed of light, while foundational to much of modern physics, might only be scratching the surface of deeper, more complex truths. Whether through quantum gravitational effects, the potential of hidden dimensions, or the exploration of new forms of spacetime, the journey to fully understand light and its role in the universe is just beginning. Each new discovery brings us closer to unlocking the secrets of the cosmos and reshaping our understanding of what is possible in the realm of space, time, and light. The speed of light is a constant that governs many aspects of the universe, but its role in particle physics is particularly fascinating. In particle accelerators, which are giant machines used to accelerate particles to incredibly high speeds, the speed of light becomes not just a reference point, but a central concept in understanding the behavior of particles at extremely high energies. The more energy a particle gains, the closer it gets to the speed of light, and this relationship is governed by relativistic effects, which come from Einstein's theory of special relativity. As particles approach the speed of light in these accelerators, their behavior changes dramatically. In the classical world, if you push an object harder, it moves faster. But when you're dealing with relativistic speeds, things get trickier. As a particle accelerates towards the speed of light, its relativistic mass increases. This means that the particle becomes harder and harder to accelerate further the closer it gets to light speed. To reach the speed of light itself, an infinite amount of energy would be required, which is, of course, impossible. This is why no massive particle, one with mass, can ever actually reach or exceed the speed of light. In particle accelerators like the Large Hadron Collider, LHC, which can accelerate particles to speeds that are a fraction below the speed of light, this relativistic effect is critical. The LHC is designed to smash protons and other particles together at incredibly high speeds to recreate the conditions just after the Big Bang. The particles are traveling at speeds where relativistic effects are profound, meaning their mass increases significantly, and the energy required to accelerate them further grows exponentially. This is why particle accelerators need enormous amounts of energy to reach the extreme speeds they achieve. For particles traveling at speeds close to the speed of light, relativistic formulas become essential to accurately predict their behavior. But while the speed of light provides a theoretical limit, understanding how particles behave when they're traveling at speeds approaching light is key to understanding quantum mechanics. One of the cornerstones of this understanding comes from the work of Werner Heisenberg, who in the 1920s introduced the uncertainty principle. This principle states that it's impossible to simultaneously know both the exact position and the exact momentum of a particle with complete precision. The more accurately we measure one of these quantities, the less precisely we can measure the other. This concept plays a key role in understanding the behavior of particles at high energies, where quantum effects dominate. For particles traveling near the speed of light, the uncertainty principle tells us that their exact behavior is probabilistic, not deterministic. This means that we can't precisely predict where a particle will be or how it will move at any given moment, especially when its speed approaches the speed of light. The faster the particle moves, the more uncertainty is introduced into its position and momentum. Heisenberg's uncertainty principle therefore becomes a crucial tool in understanding particle interactions at high speeds and the fundamental limitations of our measurements. Meanwhile, Paul Dirac, a British physicist who made fundamental contributions to quantum mechanics, formulated an equation that describes the behavior of relativistic particles. His famous Dirac equation was groundbreaking because it combined quantum mechanics and special relativity and predicted the existence of particles that we hadn't yet observed, such as the positron, the antimatter counterpart to the electron. The Dirac equation showed that, at relativistic speeds, particles could exhibit strange behavior, such as moving backward in time or exhibiting characteristics that classical physics couldn't explain. This equation opened the door to the quantum theory of fields and the study of particle physics as we know it today. Dirac's contributions were key in the development of the quantum field theory, QFT, a framework that describes the interaction of particles through fields. In this framework, particles are seen not as isolated objects, but as excitations or disturbances in underlying fields that permeate all of space. These fields are responsible for the forces that govern the behavior of particles, such as the electromagnetic field for photons and the strong and weak nuclear forces for other types of particles. QFT revolutionized our understanding of particle physics and provided a way to describe particles traveling near the speed of light in a consistent and mathematically rigorous way. The relationship between the speed of light and high-energy particles is also explored in quantum field theory through the concept of renormalization. Renormalization is a mathematical process used to deal with infinities that arise in the equations of quantum mechanics and quantum field theory, especially at high energies. These infinities come from the fact that, as particles approach the speed of light, their interactions become increasingly complex. Renormalization allows physicists to cancel out these infinities and make sense of the results, providing a way to make predictions about particle behavior that are consistent with experimental data. The work of David J. Gross and Frank Wilczek, two physicists who were awarded the Nobel Prize in 2004 for their contributions to quantum field theory, helped deepen our understanding of the strong nuclear force and its role in the behavior of particles at high energies. Their work in developing quantum chromodynamics, QCD, which describes the interactions between quarks and gluons, was essential in understanding how particles behave at the subatomic level. QCD is a key part of the Standard Model of particle physics, which provides a detailed framework for understanding how all the fundamental particles and forces in the universe interact, with the speed of light as a critical component in the equations that govern these interactions. At the most fundamental level, the speed of light sets the limit on how fast information can be transmitted across the universe. In quantum field theory, this limitation also plays a crucial role in the way that fields interact with each other. For instance, the electromagnetic field, which governs the behavior of light, is tied to the speed of light and can only transmit information at that speed. This is why the interaction of particles in a field, such as an electron interacting with a photon, can only happen at the speed of light or slower. Even in the case of extremely high-energy particles traveling close to the speed of light, the laws of relativity dictate that no information can travel faster than light, and the particles themselves can never actually reach this speed. As we push the boundaries of particle physics and continue to explore the fundamental structure of the universe, the speed of light remains a constant that underpins our understanding of the universe's fundamental forces. It is a limit that shapes everything from the behavior of particles and accelerators to the interactions of quantum fields at the smaller scales. By studying light's role in particle physics, we gain deeper insight into the fundamental laws that govern the cosmos, and perhaps one day we'll unlock even more surprising discoveries about the true nature of light and the forces that shape our reality. The study of the speed of a light has captivated scientists for centuries, and while our understanding of it is incredibly robust, the journey to fully grasp its implications is far from over. As technology advances and our theoretical models become more sophisticated, new discoveries continue to emerge that challenge our current views. The future of light speed research promises to push the boundaries of physics in ways we can only begin to imagine, opening doors to areas that could fundamentally alter how we perceive the universe itself. One of the most exciting areas where light speed may be redefined is in the realm of string theory and M-theory. These two theoretical frameworks, championed by physicists like Leonard Susskind and Edward Witten, aim to unite the forces of nature into a single, cohesive framework. String theory posits that the fundamental particles we observe are not point-like objects, but tiny, vibrating strings of energy. The different vibrations of these strings correspond to different particles, and this theory suggests that there could be multiple dimensions beyond the familiar three of space and one of time. M-theory, an extension of string theory, proposes that these strings could exist in 11 dimensions. What does this have to do with light? Well, string theory and M-theory suggest that the fabric of space-time itself might be more malleable than we currently understand. If space-time is made of these vibrating strings or higher dimensional objects, the way light behaves could change depending on the conditions of these hidden dimensions. For instance, light could interact differently in a universe with more than the 4 familiar dimensions, potentially leading to variations in how light propagates across space. This could mean that the speed of light is not a fixed constant, but could vary depending on the structure of space-time at a fundamental level. As these theories develop and we gain a deeper understanding of how they describe the universe, we might discover that light's speed is more flexible and dependent on the underlying geometry of space itself. Beyond theoretical physics, the future of light speed research is closely tied to advancements in quantum mechanics and quantum computing. Quantum mechanics, with its counterintuitive nature, challenges our classical understanding of the world. One of the most intriguing aspects of quantum mechanics is quantum entanglement, a phenomenon where two particles can become linked in such a way that the state of one particle is immediately connected to the state of the other, even if they are separated by vast distances. This connection appears to happen instantaneously, which has led to questions about whether this could allow for faster-than-light communication. Einstein famously referred to quantum entanglement as spooky action at a distance, because it seemed to defy the speed limit set by the speed of light. In quantum theory, particles can be entangled in such a way that when you measure one, the other particle's state is instantly determined, regardless of the distance between them. This instantaneous connection doesn't actually violate the speed of light limit, because no usable information is transmitted faster than light. However, the very fact that these entangled particles can influence each other so quickly challenges our traditional view of space-time, suggesting that the fabric of the universe may allow for faster-than-light relationships at the quantum level. Quantum computing could also play a significant role in reshaping our understanding of light speed. Quantum computers use the principles of quantum mechanics to process information in fundamentally different ways than classical computers. Instead of relying on bits, which can be either 0 or 1, quantum computers use quantum bits, or qubits, which can exist in multiple states simultaneously due to the phenomenon of superposition. This ability to exist in multiple states at once allows quantum computers to perform certain calculations at speeds far beyond the capabilities of classical computers. If quantum computing continues to advance, it could unlock new methods of manipulating quantum states of light and particles, potentially leading to breakthroughs in how we control and measure light itself. This might lead to applications where the speed of light is no longer the limiting factor in communication or computation. It could also open up possibilities for new forms of technology that rely on quantum phenomena to surpass current limits of speed and efficiency. While quantum entanglement and quantum computing have made significant strides, another fascinating area of research is the modification of Maxwell's equations, the set of equations that govern the behavior of light and electromagnetism. These equations have stood the test of time and remain central to our understanding of light's properties. However, Rainer Plage, a physicist who has studied potential modifications to Maxwell's equations, suggests that under certain extreme conditions, the speed of light might not be as constant as we have assumed. Plage's work proposes that, at extremely high energies, or in unusual environments like near black holes or at the birth of the universe, the speed of light could vary in ways that we don't fully understand. If Plage's ideas are correct, the implications for light's behavior would be profound. It would suggest that the speed of a light is not as fixed as we once thought, especially in situations where space-time is warped by extreme gravitational forces or high-energy environments. This could lead to new insights into the early universe, black holes, and the nature of space-time itself. It might even suggest that the speed of light could be influenced by factors we currently have no way of measuring, such as the effects of quantum gravity or the behavior of dark energy. The future of light speed research is poised to challenge some of our most deeply held assumptions about the universe. As string theory and M-theory continue to develop, we may learn that the speed of light is not an immutable constant, but rather a property that depends on the structure of space-time itself. As quantum mechanics continues to reveal its mysteries, we may find new ways to manipulate light and its speed through quantum entanglement and quantum computing. And as researchers like Rainer Plage explore potential modifications to Maxwell's equations, we may discover that light's behavior under extreme conditions is far more complex than we've ever imagined. All of this points to a future where the speed of light is not just a limit, but a key to unlocking some of the deepest mysteries of the universe. The research into light speed and its fundamental nature is still in its infancy, and the possibilities for discovery are vast. Whether through theoretical breakthroughs in higher dimensions, advances in quantum technology, or new insights into the fabric of space-time, the future of light speed research will undoubtedly shape the way we understand the cosmos and our place within it. The speed of light is more than just a number. It's a concept that carries deep philosophical and practical implications for our understanding of the universe. In both cosmology and fundamental physics, light's speed limit is often seen as the ultimate boundary. It's the unyielding maximum speed at which information and matter can travel, setting the stage for how we comprehend space, time, and even causality. But as we delve deeper into the mysteries of the universe, we begin to question whether this limit might be absolute, or if there are undiscovered phenomena that could challenge it. Philosophically, the speed of light raises fascinating questions about the nature of reality. It forces us to confront the idea that our universe might have built-in constraints, limiting how we can interact with the cosmos. For instance, one of the most profound implications of light's speed limit is the concept of causality, the idea that causes must precede their effects. In our everyday experience, this makes perfect sense. You cannot observe the result of an event before it happens. But light's speed limit, coupled with the vastness of the universe, suggests that there are limits to how far we can trace back in time. We can only observe the past based on the light that has travelled to us, and the further away something is, the further back in time we're looking. This means that our knowledge of the universe is fundamentally constrained by the speed of light, and in some cases entire regions of the universe might be permanently out of reach. Yet, as with many scientific ideas, the speed of light as a hard boundary might be subject to future revisions. We've already seen that there are theoretical frameworks which hint at the possibility of exceeding the speed of light. Take tachyons, hypothetical particles that, if they exist, would always move faster than light. While no experimental evidence has confirmed their existence, they remain an intriguing possibility within the realms of quantum physics. In fact, some physicists have speculated that tachyons could one day provide a way to circumvent the light speed limit, opening up avenues for faster-than-light communication or even travel. Even more speculative are the cutting-edge ideas in quantum mechanics that might suggest the speed of light is not the absolute limit. Quantum entanglement, for example, has been described as spooky action at a distance by Albert Einstein because it implies that particles can be instantaneously connected, regardless of the distance separating them. While this doesn't violate the speed of light limit in the traditional sense, because no usable information is transmitted faster than light, it does challenge our understanding of how information can be exchanged. Some quantum physicists have even suggested that quantum entanglement could one day lead to methods of faster-than-light communication, though this remains far from being experimentally realized. Then there's the potential of quantum tunneling, a phenomenon where particles move through barriers that they classically shouldn't be able to pass. This occurs because quantum particles don't have fixed positions or speeds, and they exist in a state of probability. While quantum tunneling doesn't directly imply that particles can exceed the speed of light, it does suggest that the rules we rely on to understand particle motion might not apply in the same way at quantum scales. Could there be yet undiscovered phenomena that allow for speeds that defy our conventional understanding of space-time? It's possible, but for now these ideas remain on the fringe of theoretical physics. Erich Jantsch's work on nonlinear time also adds an interesting layer to the discussion about the limitations of light's speed. His theory proposes that time itself is not linear and continuous, but instead might be an interconnected network of discrete moments. This concept has profound implications for how we think about light and its relationship to time. If time is not as fixed and continuous as we think, perhaps the speed of light is not as fundamental a boundary as we've believed. If time and space can be more fluid, it might be possible to conceive of scenarios where light's speed is not a strict limit, but rather a product of the structure of space-time itself, one that might be altered under certain conditions. While these ideas remain speculative, they point to the possibility that our current understanding of light speed might be incomplete, or even outdated in the face of new discoveries. The more we delve into quantum mechanics, string theory, and the fabric of space-time, the more we realize that the universe is likely far more complex than we can currently comprehend. As we continue to explore these ideas, we could uncover new ways to manipulate or understand light and its behavior, potentially bypassing current limits. The implications of such breakthroughs for space exploration would be profound. If light speed were not an unbreakable limit, the very way we approach interstellar travel could change. With current technology, traveling to even the closest stars would take thousands of years, as we are bound by the speed of light and the immense distances between stars. However, if we could somehow manipulate space-time to allow for faster-than-light travel, through mechanisms such as wormholes, warp drives, or even theoretical particles like tachyons, then the exploration of distant star systems and galaxies might be within reach, perhaps in our lifetimes. This would not only revolutionize space exploration, but also change how we view our place in the universe. The future of technology could also be impacted by breakthroughs in light speed research. If we unlock new ways to manipulate light speed, it could lead to advances in communications, energy transfer, and computation. Faster-than-light communication, for instance, would allow for instantaneous communication across vast distances, making the need for data transmission delays obsolete. This could have profound effects on everything from global communication networks to space exploration missions, allowing for real-time communication with spacecraft in distant parts of the solar system and beyond. Another area where these breakthroughs might have a significant impact is in the development of quantum computing. Quantum computers exploit the unique properties of quantum mechanics to perform computations far beyond the capabilities of classical computers. If light speed could be manipulated, or if new forms of faster-than-light travel or communication were discovered, it could accelerate the development of quantum technologies, allowing us to unlock the full potential of quantum computing. This could revolutionize industries ranging from cryptography to artificial intelligence, offering solutions to problems that were once thought insurmountable. Ultimately, the future of light speed research holds the potential to reshape our understanding of the universe in profound ways. Whether we discover particles that exceed the speed of light, uncover new principles of quantum mechanics, or develop technologies that manipulate the fabric of space-time, the next few decades of research could lead to breakthroughs that are beyond our wildest imaginations. As we continue to probe the mysteries of the cosmos, light speed will remain a key piece of the puzzle, a puzzle that may one day reveal entirely new realms of possibility for science, technology, and human exploration. The speed of light is one of the most fundamental constants in our understanding of the universe, shaping everything from the behavior of particles to the expansion of the cosmos. It defines the very fabric of space and time, providing a limit to how fast information, matter, and energy can travel. From a practical standpoint, the speed of light sets boundaries on how we explore the universe, with light being the fastest messenger we have to convey information across vast distances. In theoretical physics, It serves as a cornerstone in the equations that govern the laws of relativity and quantum mechanics. Light's constant speed underpins the very structure of modern physics, providing insights into the behavior of everything from tiny subatomic particles to the largest cosmic structures. In cosmology, the speed of light governs the size of the observable universe, while in particle physics, it dictates the relationships between mass, energy, and velocity. It's also central to our understanding of gravity, black holes, and the warping of space-time. The speed of light not only defines the limits of our observations, but also shapes the way we conceptualize the universe, the flow of time, and the very nature of reality itself. As science continues to evolve, the potential for future discoveries in light-speed research is immense. Theories like quantum gravity, string theory, and quantum computing are already challenging our traditional views of light's behavior. While we may never truly surpass the speed of light, the ongoing exploration of light's role in the cosmos could lead to new breakthroughs that radically alter our understanding of space-time, energy, and the laws of physics. The journey into the mysteries of light is just beginning, and with each new discovery, we move closer to unlocking the true nature of the universe.